Yeah, what I was saying is that right. So instead of a quiz tomorrow, what I'll do is just turn the quiz into an assignment. Just in case I want the extra time for during class on Thursday, because then on Monday we have the first exam. So I don't know if you saw the announcement that I sent yesterday. Uh, yeah, you can see the Firefox, right? So you can read it here. Well, first I already posted it on the module, so it's here also on modules if you want, if you prefer to read it from there. Um, but I also posted it here. So yeah, I posted like a study guide for the exam. We're almost done with the material. There's not that much on this exam in terms of material. Um, but in any case, I posted like the sections of, if you're reading the book, I kind of tell you what sections of the book this corresponds to, or the second book, if you're looking at that, and also the list of the PDF problems that you should pay attention to. Basically, like the format of the exam is more or less like two long quizzes. So, well, you can read it here, but it's like essentially, I would just split it into two parts. So part one goes like each part is 40 minutes long. The first part is so like part one starts at 8 a.m. Uh, three questions. Once you're done with those three questions, you upload the solutions. And then part two starts at well around 9 a.m. It's three questions. Once you're upload once you're done with those three questions, you just upload your solutions. So it's kind of two long quizzes, like basically. Um, And then, yeah, I taught this class last semester. So I posted here like the two exams that I had two classes last semester, so in the spring. So I'm posting here. I included the same topics in those two classes. So I'm posting here like the exams that they took, the solutions, and I updated slightly the list of problems to add more solutions to it. So I probably don't think I would make that many more updates to that list of problems. Um, I think it's more or less, at least for now, for the first midterm, it's ready to go. And yeah, in the spring, I was recording my classes of the spring. So I did like a class of review session. So some of the problems, if you look at, can you also see this PDF? So if you look at, yeah. So for example, some of the problems have like the solutions on that video. So that's what I wrote here. If you want to, I mean, if you get stuck, sometimes you can also find certain solutions in the video. But yeah, like if you do like the problems that are required, the exam will be more or less basically the same. Is that okay? Is that making sense? So yeah, the only thing that we really need to do left for the exam is to talk about how to solve systems of equations. Once have that done, like you'll see many problems you can automatically solve. So, and that's kind of true for like again 80-90% of the problems in linear algebra. If you know how to solve systems of equations, then you really can do like 80 to 90% of the problems of the course. Uh, they kind of become in the end just some system of equations that you have to solve. So it is kind of like something that we'll be doing over and over and over. It's kind of like only the almost like the only tool that we have in the course for solving things. Uh, so that's a good thing about linear algebra. So like I guess like you could also think about it as a bad thing, but I do like that fact that kind of everything can be done in like almost like the same way. It's just there are many interpretations for what you're doing, and that's what kind of makes it interesting. But yeah, you'll see it's not. It's kind of kind of fun. So today, what I want to start by telling you is like how to solve the systems of equations. Um, so the idea is that we're going to use these three operations that we discussed last time. So we're only going to use those three. So the three operations, like the key three operations, were swapping equations, right? Like changing like the position of the equations, which you can change, say like as changing rows, right? Changing rows, changing the positions of rows. That's kind of like the most inoffensive one because it's just like changing your mind on how you write the sentences, right? So the second equation, like the second operation, is slightly more interesting, which is just multiplying a row or an equation by a non-zero number, or multiplying, dividing. Oops. My cat likes keywords. Multiplying, dividing um, a row by a non-zero number. Okay, and the last operation, that's kind of like the most interesting of the three, actually. So this is the most interesting one. Is that you can combine equations together, right? Like add equations together um, with with the extra benefit that you can multiply one of the equations by a number. So you like I can write it like this: like you can add a multiple of one equation to another equation of one row. When I say row or equation, I kind of mean it as synonyms. So saying a row or equation are kind of the same for us now. Add a multiple of one row to another row. Okay. So every problem that we're going to solve today is essentially doing these three things over and over and over and over. Like you'll see, like there's no everything can be solved in this way. And the goal, so again, like the goal is to get the matrix to something that's called the row echelon form. So let me explain what that means. Like in practice, like the definition is kind of like I'm just going to write it because I feel like I should, but kind of is once you have like a concrete problem, you'll see it's kind of clear what you need to do, even if you didn't know the definition. But it's kind of good to have it around. Uh, but you'll see it's kind of like you will feel what that you are. It is like these problems do give like a sense of like a feeling that you are. Once you get a point to where you're done, you will notice for sure that you got to the end. It's not they're not tricky in that sense. But I still I'll give you like the definition. So the goal is to use these three operations to get to the row reduced echelon form. So the goal is to use these operations to get to the, let me use a different color, row reduced echelon form. Of the matrix. Okay, so what does that mean? This means, like again, the definition, it will be less important than what it seems, but I'll just going to write it anyways. So this is kind of like a way you want to present the system of equations so that it becomes clear how to solve it. So the first thing that you want to do, more like for aesthetic purposes, is to have like all the rows with all the rows whose entries are a bunch of zeros to go at the bottom of the matrix. So every row whose entries are just zeros consist of just zeros get appear at the bottom of the matrix. So just to give you a very simple example, if I write something like this, I don't like this. This is bad because this zero row is at the top. So what is the good way? The good way is to send it to the bottom. So 1 0 0 0, this is good. Okay, and I mean that's like, for example, one of the purposes of like this operation of swapping rows or swapping um or swapping equations, just to I can like, well, I can put it out in the augmented version. You'll see what I mean by that. If you thought about it as a system of equations. So, well, I mean, let me put it like this before. Okay. So this is like, so everything, the moment you have to see a row with a bunch of zeros, send it to the bottom. Okay. Again, this is more for aesthetic purposes. So it's kind of easy to remember. Okay. Then also for us, like this is more like useful, is that the first non-zero coefficient of a row is 1. The leading, like what's called the leading term. So the leading term of a non-zero row is 1. So leading term just means the first coefficient that you see when you read the row from left to right. So leading term, this is just this is the first coefficient of the row. First non-zero coefficient of the row when you read it from left to right. So for example, again, if I gave you something like, let's see. Okay, something simple like that. This is bad again. Now this is, at least now this is satisfying the rule that, you know, the zeros should be at the bottom. So this is good now, but it's bad because the first non-zero entry of this row is 2, and it should be 0. It should be 1, right? And the first non-zero entry of this row is 3, but that should also be 1. So what do? You do the operation of killing. I'm sorry, of multiplying the equation or the row by a number to make it once. So it is you just do it like 1 0 1 half 0 1 1 3 4 thirds 0 0 0, and this one is good. Is that making sense how I got from here to here? So like what I did in the first row was just multiply by 1 half, right? And what I did in the second row is multiplied by what, by 1/3, right? Is that making sense? Uh, so again, it's kind of like we're trying to put, it's kind of like putting what we're actually trying to do is kind of put as many zeros as ones as possible. Okay, so so far so good. Any questions up to this point? Again, like in practice, that's kind of what you probably would end up doing anyways if you didn't have this definition, but I'm just writing it out explicitly. And there are just two more conditions, which are again kind of intuitive, which says that whenever a column contains the non-zero entry of some row, all other columns are 0. All other entries on that column should be 0. Okay. So let me explain what I mean by that. So just to keep working with these matrices that we have, like, let me put like a similar matrix to the ones that we have here. So if I had something like, okay, imagine, okay, let me put it like a 1 as well, just for, and let's put a 2 here, actually. Okay, so imagine that your matrix now looks like this. Okay, so what's going on here? So this row starts with a 1, so that's good. This row starts with a 1, so that's good. This row starts with a 1, so that's good. But for example, for this one, right? For this one, if you look at the other entries in the column, right? There are zeros and zeros. I mean, there are numbers which are not zeros here and here, right? So the idea is that this is bad. Now this is bad because we want to see like only one per column whenever it's like a leading entry. So this is like a leading entry for the second row. So every other entry in this column except for this one should be 0, basically. So I want to make this one 0 and this one 0. Is that making sense? Again, you should just think that you're trying to get this to look as much as possible as the identity matrix. And if you think about it, um, so what if it happens to be like, well, it depends on you might have a non-zero value above I mean, you can always reach the row reduced echelon form. So it depends. I guess you would have to think. You mean like in a case where you might have a non-zero value above? Well, like for example, here I have a non like that's what I'm going to do now. I have here like a non-zero value above a non-zero entry, right? So I'm going to get rid of it, but you can always get the row reduced. I mean, otherwise, like it would be a problem. Like this would be a problem. But yeah, no, it does. I mean, yeah, if you think about something concrete, maybe I can help you out, like to see where the where you think the problem is. But you will see that once we start doing the examples, there's no way to avoid. You can always get this to work. That's a uh, right. So what you have to do here is you want to put a 0 here and a 0 here. So how can you put, like let's think about the first one. How can you put a 0 here? In terms of the operations. Remember, there's only an operation of the three operations, there's only an operation that helps you can help you put zeros, right? So which one should that be? What would you do?
-2.
You can do -2 row 2, right? and add that to row one, and you're going to replace that in row one. Is that making sense? So let's think it out. So I'm going to multiply every entry of this row by -2, right? And add that to the first row. So let's see how that works. Good. Let me space them out a little bit more because I may need a little bit more space. So you copy the coefficients of the first row. And so you're going to subtract -2 the second row. So it becomes -0, and then 2 minus 2, right? And then you're going to subtract -2 of the second row, so it's 2 minus 2 as well, right? Is that making sense? So in green, I'm just multiplying. In green is what you get from doing the coefficients here by -2. Is that okay with everyone? I'm going to write the next step. But there's also we also can, if you want, you can also put like a 0 already here. So how can you do a 0 there? Well, you can do, for example, minus row 2 plus row 3 and substitute that into row 3. So again, let me copy first the original coefficients. The original coefficients are 0, 1, 4, and then yeah, it's always possible to, yeah, you can always achieve the row reduced echelon form. Yes. And then you are subtracting -0, -1, and -1. Is it making sense that that's what the operations look like? And then you get what? You get 1, 0, 0, right? When you simplify this, you get 0, 1, 1, and then you get 0, 0, 3. Is that okay? That's what you get with this matrix. And then now, what's the I mean, we might finish this one like so that why do you have to -2 in column 3? Let's see. Oh, because you mean this -2? Because every coefficient of row 2 was multiplied by -2. It has to affect every coefficient of the row. You cannot just change an individual coefficient. The operation is done on the entire row. So everything here gets multiplied by -2. Well, it depends. Well, I mean, you mean here? Uh, like, right, like you're saying, why not in the left column? Well, but in the left column, I subtracted 2 times 0. I mean, is it the 2 times 0 is 0, right? I mean, you can write it if you prefer, like 2 times 0. I don't know if that's what you mean. Yeah. I mean, it's just that 2 times 0 is 0, so that's why I just wrote it as 0. But if you want to read it, like put it more explicitly, you can put 2 times 0. Is that making sense? Yeah. So just to clarify again, in these operations, like that's the only thing you have to be careful. In these operations, every single coefficient of the row gets affected by that number. When it's 0, I mean, usually, yeah, you skip a little bit of the steps, but yeah, it is, it's like that. And now, okay, so now you could ask, is this like in the version that will, if imagine you get to this matrix, would this be the matrix that you want? Like, or is still under these new conditions that we're asking, there's still something that you have to fix here, right? It's still not in the most simplified version, right? What can be Now it satisfies that all that there's zeros here, but there's still if you compare to the other requirements I put earlier, there's still things that you can fix for this matrix. What's something you could fix here?
I think 3.
Yeah, we don't want to see a 3, exactly. We want as many ones or zeros possible. So to make a 3, you just, yes, you just do 1/3 of row 3, perfect. So let's do 1/3 of row 3. And so you get 1 0 0 0 1 1 0 0 1, right? So you get this. Is that making sense? And now there's still something that can be fixed in this one, right? What else could you do? The problem is that we don't, again, like once you have a 1, you don't want to see any other ones in that column. Once you have the first 1 in a row, you don't want to see any other ones in the corresponding column. So you have to kill this 1, which again, it makes sense if you just think about getting as much as possible to the identity matrix. And so like here, to kill that 1, you could do like minus row 3 plus row 2, right? Row 2. Again, this is 0 minus 0, right? 1 minus 0. 1 minus 1. And then this is 0 0 1. And this is 1 0 0 1 1 0 0 0 1. Okay. Is that making sense? And now this is actually good. This is really what we're something like this would be what we're after.
Professor, why we
Mhm.
still simplify the second rules again?
This one? You mean
Yeah, the negative R
this?
R3 plus R2.
The thing is like the idea is that once you have 1 in the first, this is the first row, this is the first one of the third row, right?
Mm-hmm.
Once you have a 1, you don't want to see any other ones in that column. So you see there's like a 1 on top of it.
Okay, so each column only can have the 1.
There can only be one. Okay. How should like it is like okay. Let me once each column can only have one above if that column corresponds to a leading entry. So for example, let me clarify this. Like if you had something like this, right? Right? If you have something like this, here's another example. If you have something like this, you could say, well, there's a 1 here, right? And there's a 1 on top of it, but that's fine because this is not the first one of the second row. You know what I mean? So it's only for the first one that you cannot see any other ones on that column. So this is the second one in the second row, and so that's why it's fine that there are other ones above or below it. Or likewise, you can think that this is the second one of the first row, and that's why it's fine that there are ones above or below it. Because like the thing is like there's no way, there's no way to get a 0 here without like putting I don't know if this makes sense. Like, how could you make a 0 here? Well, you would have to subtract the rows, but the moment you subtract the rows, then you change this one into something non-zero, right? So there's no way kind of to, like, kind of this is the most number of zeros that you could have in this matrix. Any other operation that you do can delete put a 0, but you kind of create something non-zero elsewhere. So what I'm saying is that this rule is only for the first row. Sorry, for the first one of the row. So this is fine So this one already is good because what I mentioned, because the previous rule only applies to the first one of each row. Is that making sense?
Yes.
I mean, again, in practice, you don't get confused by this. Like, kind of like writing it as a definition can be more confusing. Like in practice, like once you get to this point, right, you would think, okay, what else could I do? And you would notice, like, if you try to make a zero here, there's no way to do that without creating something non-zero here. And like similarly, if you try to create a zero here, there's no way to do that without creating something non-zero here. So you just realize that you're kind of like, you would get stuck, and that actually means that the process terminated. And this would actually be what we are calling the row reduced echelon form. Does that make sense? So it's, I mean, again, like it's really in practice a lot less confusing. You'll see once we start doing the examples. It's just that when you list all the conditions, like it seems like a lot to remember. But if you just think about getting as close as possible to the identity, then that makes more sense. Like, because it's just, by that I just mean getting as many ones and zeros. And then you see like that this is kind of like the best thing you could do in terms of ones and zeros. Okay, and then there's just one final condition. Let me see, where should I? Okay, and then again, the last one sounds a little bit too. So this is the last condition. So call it D. Again, it sounds a little bit weird, but once you see it on the example, it's a lot more clear. So the leading entry of a non-zero row lies in a column to the right of the column containing the leading entry of the preceding row. Like more pictorially, like let me write this like kind of put in parentheses what this means more in terms of a picture. It means kind of like the leading one to look kind of like in a descending staircase. Like that, I think is more clear. So let me write it here. Like the the leading terms, the ones which are the leading terms of the rows should be arranged in as a descending staircase. And you'll see what I mean by this with the picture in a moment, with the example. But again, so something like this. Yeah, so let me give you a second to copy this. So here's an example. Like if you had this matrix, let me put a 3x3 matrix. Like I'll put two 3x3 matrices. So if you had something like this, okay. What's the pro? Okay, so this one is bad. Why? Because in a sense, like if you draw like a staircase, I mean it's better as a picture. If you draw a staircase, oops, connecting the ones, right? You see, like you kind of have to climb up the staircase from the first one to the second one. Is that making sense? Uh, you kind of want the staircases to go always like decreasing your height. So how could you do that? You can switch the rows. So if you switch the rows, now the staircase of ones looks like this, which is kind of descending. Is that making sense? Here's another example. Ooh, let's see if I can think about this one. Okay, so let's think about this one. Again, I'm just trying to do some simple ones so that you see like the idea. Why is this one bad? Because if you draw the staircase, right, from this one to this one, you go down, which is good. But then from this one to this one, you have to climb up again. Is that making sense? So we're kind of zigzagging all over the matrix, and we don't want that. We kind of always want to drop the ones. We want the ones to be dropping in height. So again, how can you do it? That's the point of the operation of swapping rows. So to fix this, you just swap the second and third row, and so you get 1 0 0 2 0 1 0 0 0 um 0 0 1 0 0 0 0 0. And so you see now it looks good. Boom, boom, boom. So it now looks descending. Is that making sense? I can put like I can draw the staircases for you here if you want. I mean, in practice, again, it is there's not too much of a chance of confusion. I can promise. I mean, you'll see once we start doing this. It's very clear what to do at every single step. It's just you write all the conditions. It may look like a little bit too overwhelming, but you'll see that that once we start doing like the examples I'm about to do, it will look a lot better. And this is all that you need for to understand how this matrix, how to reduce a matrix. So the goal is to apply operations 1, 2, and 3 so that our matrix has those properties that I just wrote. Okay. So in a sense, like the row, like the idea, is that the idea is that like the row reduced echelon form of a matrix is like kind of like the matrix with the most ones and zeros that you can get of the original matrix. So the row reduced echelon form is the matrix with the most ones and zeros of the original matrix out of the original matrix. Which also looks as close as possible to the identity matrix. Is that okay? Is that making sense? So, okay, let me pause here to see if there are any questions up to this point. So the last definition before I start doing the examples that I want to give you, kind of is convenient to keep it around. It's called the rank of a matrix. So this, I promise the last definition before doing the examples. So rank of a matrix. It's a very easy definition, but it's kind of convenient, you'll see, to use. So the rank of a matrix is just the number of non-zero rows of the row reduced form of A. Okay. So essentially you get A to to this reduced form and count the number of non-zero rows, and that's the rank. So I'm about to, I'll compute the rank for all the examples I'm about to do next, but just to give you like a quick one. So let's say that the matrix I had given you, just to make it easy, is something like this. Okay. So the question is, this in row reduced echelon form, yes or no? Is this already completely simplified? I guess that's what I'm asking.
No, still no.
No, right? Yeah, so what could you do first, for example?
Simplify the 2 first.
These two, you mean?
Yes.
Actually, that's kind of at the in a sense, you kind of want to move more like this along the matrix, roughly. So you kind of want to go like from column to column. So the two to get there, we kind of have to do a lot of things before getting to that too. The cleaning process is kind of more like go through the first column, then second column, third column, and so on. So yeah, like if you follow the thing that I'm just saying, like the first thing you could do is get rid of this one, because the first row is already good in the sense that it starts with a one. So since this one starts with a one, we cannot see ones anywhere else. So yeah, you could do like minus row 3, minus row 1 plus row 3, and I'm going to replace that into row 3. Is that making sense? So let me do it. Show you what that looks like. So again, we're just going to subtract row 1 from row 3, and so you do 1 minus 1, you get 0. Then 1 minus 0, you get 1, and then 5 minus 2, you get 3. Is that making sense? Any questions of how about? So I'm going to put a 1 here. I want to put a 0 here. So to put a 0 here, I can take the 1 from here and subtract it to get a 0. So that's why I'm going to do minus row 1 plus row 3. Is that okay? You have to be careful about that. We'll get to do that in a couple of minutes. You have to look at the ranks, but it more yes and no. But so what I'm saying is that like I'm going to put like I'm doing minus row 1 plus row 3. So what is row 1? Is 1 5. And I have to subtract row 1, so it's 1 minus 1, 1 minus 0, 5 minus 2. I'm not sure if that's more clear. Because again, you need to get a 0 in here. I want to see a 0 here. So the way to get a 0 is to do this operation. Is that making sense? If plus row 3 just means that you're multiplying every coefficient of row 1 by minus 1, and you're adding that to every coefficient of row 3.
We are not finished the most simplifies yet, right?
Sorry?
I mean, we didn't finish yet, right? For the
Yeah, we haven't finished yet. Yeah, I'm just
Okay.
explaining. This means like multiply every coefficient of row 1 by minus 1, which is what you see here, and add that to every coefficient of row 3, which is what you see here.
Yeah. Okay.
Or if you want, like, oops, let me see if I could write it in the opposite order. Like it is because I wrote minus 1 first. So it's minus 1, minus 0, minus 2, but that's being added to row 3. So it's plus 1, plus 1, plus 5. I don't know if that looks better. So it just means minus every coefficient of row 1 plus every coefficient of row 3. Is that making sense? So this is how you get 1, 0, 2, 0, 1, 3, 0, 1, 3. Well, it's not always well, it depends why it's always the last row. It's just like you kind of you know, like in the previous example, didn't I do an example where let's see. Oh, like for example here, if you look at this example that I did here, I did minus 2 row 1 plus row 1. So I did that in the first row. So I'm not always doing it on the last row. It is true that many times the last row is the one that gets affected first. But I mean, this was like an example where, you know, I also did like the operation to the first row. Because here I wanted to see a 0 here, and to get a 0 here, you had to do minus 2 row 2 plus row 1. So yeah, it's not it's always to the last row. Sometimes like it does happen to be true that many times like the last row is affected, but yeah, it doesn't have to be necessarily the last row. Yeah, but it's still, this one is not fully simplified yet. Why? Because there's a 1 here, but if you look at this one, you have to, because of this one, you have to put zeros everywhere else in this column. So how can you make a 0 here? What operation would you do? Oh, you could do minus row 2 plus row 3 into row 3. Then you get, again, this gives you, let me put it here, minus 0, minus 1, minus 3, then plus 0, plus 1, plus 3. And then what? You get 1, 0, 2, 0, 1, 3, 0, 0, 0. Well, remember, it is not allowed to multiply by 0. It's not allowed, you know, the rules do not allow to multiply by a 0 number. Sorry, the rules only allow to multiply by a non-zero number. You cannot multiply by 0, because multiplying by 0 kills all the information about the equation, right? Everything would become 0 equals 0 always. So it is not, I mean, multiplying by 0 kind of eliminates every information that you had about the equation. You know what I mean? Like, imagine, like, you could make this, like, write it down more concretely. Like, if you had like an equation that's like 2x plus 1 plus y equals 3, right? If you multiply both sides by 0, which is kind of what that corresponds to, you get 0 equals 0. And so you cannot recover the equation, right? Remember that we're trying to do operations that you can always undo. So if you multiply by 0, how could you undo that operation? You would have to divide by 0, but you cannot divide by 0, you know? Is that making sense? Yeah, so like the important thing of this process is that every single operation can be undone. And multiplying by 0 is like a irreversible thing. You cannot take it back. Is that okay?
That's why I had a question as well.
Uh-huh.
So I know the row 2, second row plus the row 3 or something, it works here. So for example, if the row 1 also, works for the row 3, can I just use the, for example, maybe just negative R1 plus R3 if the first row is work?
I mean, if the first one row had worked again, then yeah, you could have used it again. But or you say like, well, for example, in this case, it wouldn't have mattered in which order you did it. But yeah, sometimes like if the matrix is more complicated, like the steps can appear in different order, or could be applied more than once, if that's what you mean. But yeah,
Sorry, because I don't know when I should use the to use the R1 or R2 to get R3. I just don't know.
well, it's that you have to, like, the matrix will tell you what to do because a matrix wants as many ones or zeros possible. So that's what determines the operation. So it like you once you look at a specific matrix, that's the one that it will tell you what operations to do. Like again, once you start doing once we do more examples today, you'll see it's not so. It is less controversial than what it seems. Like it is, like the coefficients of the matrix is kind of what will determine what operation you want to do. Like you'll see, it's not. It's less confusing, like from that perspective. Like you have less choices than what you may think you have. Like it will be more clear once you do a couple of examples and you realize that what operations you have to do. But yeah, if you just follow the principle of putting as many ones and zeros possible, then they're like it's very like not straightforward, but it is very few choices that you have for doing that. So it's not like you will be in conflict on what to do. Like if we yeah, again, like once we'll do more examples today, you'll see it. But my point is that if you look at this matrix, if you look at this matrix, you started this way and you get it to this version, right? So now, can this be simplified any further? Not really. Because, for example, there's no way to put a 1 here without destroying this 1. Like to put a 1 here, you would have to multiply by 1/3. But once you multiply by 1/3, that this stops being a 1, and so on. So you kind of have to realize that this is kind of like the most simplified version. So this is like the row reduced echelon form of the matrix. Okay. Of A. And so what's the rank? The rank of the matrix is then the number of non-zero rows. So in this case, what is the rank of A? So you have to count how many non-zero rows you have at the end of the process. So what's the rank in this case? Well, we have one non-zero row and we have a second non-zero row, so the rank is just 2. Because there are 2 non-zero rows. So like the whole point of this example is just to make you realize that the rank, you cannot identify the rank from at the earliest stage, because at the earliest stage, you have 3 non-zero rows. You have to reduce the matrix until you get to a simplified version, and then you count the rank. Okay, so the rank can only be determined at the latest stage. Is that making sense? So yeah, let's take okay. So now I kind of gave all the theory that I needed to give. So let's take a 5-minute break, and when we come back, I'll just do more examples of these reductions, because everything else kind of just depends on that. So I'll do more examples, and I'll show you how the different possibilities look like. For how can you identify when the system has 0 solutions, infinite solutions, or not a unique solution. Yeah, but let's take a 5-minute break and we'll start doing that once we come back. Okay, so let me start giving you some examples about solving systems of equations. So first, as I said, when you have a system of equations, only 3 things can happen. Either you have infinite solutions, a unique solution, or no solutions at all. The one that's easiest to understand is the one where there are no solutions. So let's start with that. So here's an example. Okay. Okay, so let me see which one can I give you. So, oh, okay, this one is nice. Yeah. So let's do this one. So I want to solve x plus 2y plus 3z plus 4w equals 5, x plus 3y plus 5z plus 7w equals 11. And then x minus z minus 2w equals minus 6. Okay. So let's say you wanted to solve this. The thing that you always have to do first is to write it in the form ax equals b. Okay, so you have to find the form, write it as ax equals b. Okay, what is the matrix A? The matrix A is just the coefficients that appear on the left-hand side. So what are the coefficients here? Are 1, 2, 3, 4, 1, 3, 5, 7, and then 1, 0, because there's no y in the last equation, and then minus 1, minus 2. Is that making sense how I got the matrix A? So if you want, and then the right-hand side becomes just a vector. Okay, so this makes sense because this is 3 by 4, this is 4 by 1, and this is 3 by 1, and so it does match the sizes of the matrix multiplication that I had given you before. And if you do the dot products, right? If you do the dot product of this with this, you'll get the first equation. The dot product of this with this is the second equation, and the dot product of this with this is the third equation. Is that making sense? Are there any questions up to this point? So once you do that, the next step is to like that again, like keeping XYZW is kind of annoying. You don't get anything from it. So the next step is just to change that into the vertical line. So all of this just becomes a vertical line. So that way you only work out with the numbers, the coefficients. So you just write it in this version, and this is the version that we will work with. Okay, so again, just think of this vertical line as representing all of this junk. Okay, so E is that. And once you get here, then you have to start simplifying the matrix. Okay, so again, you want to make as many ones as zeros as possible, and you kind of read the matrix in a sense like by from the columns. It's kind of, or I mean, it's kind of like a process which goes from left to right. In a you know, it's like a sweep out of the matrix, but it always starts like from here to everywhere else. So if you start with this first coefficient, you see that it already has a 1, so that's good. So once, oops, this looks like a 10, like that 0 should be here. So once you have a 1, the goal is to make zeros everywhere else on that column. Okay, you can, once you have that 1 here, you want zeros everywhere else in that column. So that means that I don't want to see this 1, and I don't want to see this 1. So how can you make those into zeros? What operations could you do? How can I make a 0 here?
Negative 1R1 plus R2, got a R2.
Yes, perfect. And how could okay, so let's copy this. You can actually do the two operations at once. So let me just copy the first row, which is the one that we're going to use to simplify the others. So yeah, this is the one that we're going to use to take care of the second row. And then how could you make a 0 here? It's kind of the same, but adding it to row 3, right? So you can do negative R1 plus row 3 into row 3. Is that making sense? So I'm going to use this 1 to kind of kill this 1 and kill this 1. Okay, so that just means like I can put it for you. I would put -1, -2, -3, -4, -5, and then -1, sorry, -1, -2, -3, -4, -5. Right, that's every coefficient of the first row multiplied by -1, and I'm going to add that to the corresponding row. So +1, +3, +5, +7, +11, and then +1, +0, -1, -2, -6. Of course, in practice, you don't have to write everything so explicitly. So people, once you get used to it, like you may skip this step, but it's kind of nice to see it written down, especially at the beginning, like all together. Okay. So far, so good. So this gives you 1, 2, 3, 4, 5. And what do you get when you do these operations? You get 0, 1, 2, then 3, then 6, right? And then 0, -2, then -4, -6, and -8. Is that okay? Is that making sense? Okay. Now, you kind of are done with row one, with column one. Column one is ready to go. Now you look at column two, okay? If you look at column two, you also look at, I mean, you kind of look at the second row, because like already like the first row had its first entry being 1, so the first row is sort of good to go. But now you look at the second row. So the second row starts with a 1, which is good. So since this one starts with a 1, you want zeros everywhere else in that column. So you want a 0 here and you want a 0 here. Okay? So you need a 0 and a 0. And how can you put zeros? You only have one operation to put zeros. So you do, how can you put a 0 in the here? You can do -2 row 2 plus row 1, and I'm going to replace that into row 1. And how can you put a 0 here? You can multiply this by 2, so you get 2 row 2 plus row 3 into row 3. Okay, so let me copy this again. So again, like row 2 is the one that I'm using for everything, so you can copy that one first. So then you multiply by, in the first one, you multiply by -2, so you go -0, -2, -4, -6, -12. And in the last one, and then you are going to add that to +1, +2, +3, +4, +5. And then in the other one, you get what? You get 2 row 2 plus row 3. So you get, you multiply the second row by 2. So you get 0, 2, 4, 6, and then 12. And then you add that to the row 3. So +0, -2, -4, -6, -11. Is that making sense how I'm getting these numbers? Like, here's also a good moment to observe that every individual operation is not too complicated. It's like adding or adding or multiplying, but then you're doing it many times. So there is a chance of mistakes just because you're doing it so many times. So it's always good to double check that you are putting the right numbers, because if you mess up one of these numbers, that can affect the entire solution. So it is always good to double check that you're doing that there are no mistakes in the multiplications or the additions that you're doing, because you're doing it so many times, and if you find a mistake later on, it's kind of hard to undo it. So that is a tricky part of these problems, just that fact. So just be careful about that when you're doing these simplifications. Always double check what you're doing. Okay, we're almost there. Almost there. What else is left? What else could you do? Almost here. So column 1 is done. Column 2 is done. What about column 3? Well, there's no way to put a 1 here or a 1 here without messing up the previous coefficients. So you cannot really touch them. And by the same idea, you cannot put like a 1 or a 1 here without affecting anything from before. So there's not really a way to simplify these two columns. Like these columns are what they are. there's still something else. There's still some simplifications you can do in this on this end, right? If you wanted, so you could put like zeros on this above this one. So how can you put zeros above that one? You can do minus. Let me see which colors I have in use. You could put minus row 3 plus row 1. Sorry, how you would need 7 row 3 plus row 1 into row 1. And then you could also do minus 6 row 3 plus row 2 into row 2. So again, like the one that I'm going to leave now untouched is 0, 0, 0, 0, 1. And then you get 0, 0, 0, 0, because and then 7. And then you get 0, 0, 0, 0, and then you get 6. Oh, sorry, minus 6, because this one is minus 6. And then you add them to the. Also, you get 0, sorry, you get 1, 0, minus 1, minus 2. And this one gives you what? 0, right? And then you get 0, 1, 2, 3, 0, and 0, 0, 0, 0, 1. Is that making sense? And again, just to emphasize this, you can, like the nice thing about these matrix problems is that you can always verify them on the computers if you wanted to. For example, just to go, I don't know if you see one from Alpha. I had showed you yesterday you can use this row reduce operation. So you can go to Wolfram Alpha and enter the original coefficients of the matrix we were working with is 1, 2, 3, 4. And then you have to put like also the vertical line. So put 5. The vertical line is not enterable from Alpha. So you just put like a comma for the last one. Then you get 1, 3, 5, 7, 11. And the last one, what is 1, 0, negative 1, negative 2, negative 6. So hopefully this matches what I wrote. You just imagine that there was this vertical line between the fourth column and the fifth column, right? But if you look at it, if you do the row reduce, it gets you to the coefficients that we have here, right? It's 1, 0, negative 1, negative 2, 0, 0, 1, 2, 3, 0, and 0, 0, 0, 1. So it's always like the nice thing about this is that it gives you like an infinite number of problems you can work on because you just start changing the numbers in the coefficients, and then you can double check what you should get in here. Is that making sense? So it's good resource to know that you have around.
Professor, you say we can use the 0 to multiply the rows, but why here we use the 7 times R3?
Well, what I was saying is that you can never multiply by 0, right?
Yeah.
But I never multiply by 0 here, right? I multiply by 7 and minus 6. So it's just that you do want to get zeros, right? You do want to see zeros, But to get zeros, you get to those zeros not by multiplying by zero, but by combining the rows in different and useful way, right? But I never multiply by a zero here. It's just that if
Oh,
you go
I can just like 0 times R3 kind of
right,
like
and right, it's
um,
like doing 0 times R3 would do nothing, right? Because it would be like adding 0 to everything. So you get back that
Mm.
same row. So I mean, that is more or less okay, but it's not useful. Like you really should think that 0, it's better to think that 0 is not allowed anywhere. Like, because if it's multiplying, like if you had put 0 times row 3, what's the point of doing that, right? Like it's adding 0 to every coefficient, like you don't get anything nice. So it's always, and if you multiply a row by 0, then you completely destroy that row. Like you cannot undo it. So yeah, in all the operations, if you check all the operations that I did, the numbers were always non-zero. So you have to
Mm.
stick with that. Is that making sense?
Yes, gotcha.
Okay. And now finally we get to this system. My claim is that this is the row reduced echelon form. First, let's check what this looks like in terms of the system of equations. It gives you 1, 0, -1, -2. Once you are done reducing the matrix, you can kind of like on high show what this vertical line represented. So this vertical line represented the vector XYZW. Okay. So what does this? Okay, so that's like actually what this means. So like this really means the same as this. But that you can rewrite as a system of equations. And it's easy to rewrite it because they're just like the coefficients in front of x, y, z, w. So you just get x minus y minus 2w equals 0. Y plus 2, z plus 3. Oh, sorry. X minus z minus 2w equals 0. Then y plus 2z plus 3w equals 0. And then the one that's more interesting is the last one because it gives you 0 equals 1, right? Because every single coefficient here of the variables is multiplied by 0, right? So it's like putting 0x plus 0y plus 0w plus 0c, right? So first, like, I mean, hopefully there's something clear that's happening here. But first, just compare these equations versus the original ones, right? They're a lot less, they're a lot more simple. And it also now, once you did this, like it also is showing you something that is going wrong, right? So what is the problem that you see here? Yeah, 0 equals 1. That cannot happen, right? This cannot happen. This is impossible. So that's so basically that's like shows you explicitly like that the system is inconsistent. So this system cannot be solved. So there are no solutions. Is that making sense? What? So how can you identify? Okay, so how can you identify the case where there are no solutions? This is what will always happen. You will always get a row of zeros followed by a non-zero coefficient when you write that system of equations. So how do you identify a system with no solutions? You will get to a 0 row, to a row full of zeros, followed by the vertical line with a non-zero number next to it. So like the inconsistent systems always look like something like 0, 0, 0, 0, blah 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 zeros, and then here like a 1, for example. This is how all the inconsistent systems look like. This is how they always look like. So they're very easy to identify once you get to the row reduced echelon form. Is that making sense? So it just I think there's no way to get lost with an inconsistent system, because once you rewrite it to the system of equations, if you prefer to see it that way, you'll get something silly like 0 equals 1. That's basically what it will always happen. Like you always get like 0 equals 1 or 0 equals 2, something like that. Like, but I mean, you can always make it 0 equals 1 because you can make this entry 1. So it will always say 0 equals 1 when you rewrite it as a system of equations. So there will always be an equation. Okay. Okay. So this is like the way to identify the inconsistent systems. That's um, again, those are the easiest ones. So it's just a row full of zeros followed by something non-zero after the vertical line. That's always what happens. So there are two other examples left, which is the unique solution case and the infinite solutions case. So let me go next with one of those. Let me go first with maybe the unique solution. Okay, so here's an example of a case with unique solution, so that you see how it looks like. So let's see. So let me give you this system of equations. Okay, so 3x minus b equals 3. So I'm going to give you this system of equations. Let me just double check it to make sure this is going to be fine. Okay, yeah, this should be fine. Okay, so now let's try to see what happens here. So again, you have to write it down as a matrix version, 1, 2. So there are only 3 variables here, x, y, and z, right? So it's 1, 2, 3, 2 minus 1, 1, 3, 1, 4. 3, 0, negative 1. This is times x, y, z equals 9, 8, 17, 3. And that makes sense because what? This is 4 times 3. This is 3 times 1. And so you end up, after you do the multiplication, you get something of size 4. Sorry, let's see. Yeah, 4 times 1, which is fine. Okay. So now let's, again, when you are solving this system of equations, this is like junk. You don't need to be writing it every single time. You will just lose time. You will just waste time and space. So you put the vertical line. By the way, the matrix, so this is again like the matrix A. This represents the matrix A. This is called the matrix, this is the vector B, right? And these two together, like A followed by the vector B, is called the augmented matrix. So, I mean, it's just a piece of terminology, but this one is called the augmented matrix. So it's the matrix together with the vector. So and it's sometimes written like A vertical line B, which makes sense. So okay, and now I want to reduce this as much as possible. I already have a 1 here, which is good, and so I have to put 0, 0, 0. So I got to clean the first column first. To do that, I'll do what? Let's do it here. Like I'll do minus row 1 plus row 2 into row 2. I'll do minus 2 row 1 I should do. I'll do minus 3 row 1 plus row 3 into row 3. And I'll do minus 3 row 1 plus row 3, row 4 into row 4, right? Because there's 1, 2, 3, 4 rows. So let me see if I can copy this. So the first one is minus 2, so it's minus 2, minus 4, minus 6, minus 18. Then I'm going to do it with minus 3, so it's going to be minus 3, minus 6, minus 9, minus 27. And then I'm going to do it with minus 3 again, so it's minus 3, minus 6, minus 9, minus 27. And again, that is going to be added to the previous entries in each row. So my plus 2, minus 1, plus 1 is 8. Plus 3, plus 1, plus 4, plus 17. And then plus 3, plus 0, minus 1, plus 3. Okay. So let's see what that gives us. It gives you 1, 2, 3, 9. So you get 0, minus 5, minus 5, then minus 10, and then you get 0, minus 5, minus 5, minus 10, right? And then you get 0, minus 6, minus 10, and then minus 24, if I'm not mistaken. Is that making sense? So far so good? Now, there's something very obvious that you could do here before we continue. I don't know if you see there's kind of something you can notice maybe about the second and third rows. They're exactly the same, right? So, I mean, if you want, once the rows are exactly the same, you can just like make one equal to 0. How can you do that? Like you can just do minus root 2 plus root 3, for example, before doing anything else. And that will make it put a bunch of zeros. 1, 2, 3, 9, 0, -5, -5, -10, because they're exactly the same. So it will just become 0, 0, 0, 0. And then 0, minus 6, minus 10, minus 24. Okay. So once you have two repeated rows, you can immediately make one 0, basically. They kind of represent the same equation, so you are recounting it. And then this is a good example where we got like a bunch of a row bunch of zeros, so you can move it to the bottom. So to move it to the bottom, I'm going to change row 3 with row 4. So I'm going to change row 3 changes with row 4. And I also want a 1 here. So I'm going to put like 1 minus 1/5 of row 2. So to get a 1 here. So once I do that, let's see what this looks like. So I get 1, 2, 3, 9. So once I'm changing rows 3 and 4. So the row of zeros goes to the bottom, 0, 0, 0, 0. And then the other one now goes here. So let me put it like in blue. And then once you multiply this by -1/5, you get 0, 1, 1, 2. Okay. Okay. And once you get there, then you can use this one to put zeros and zeros again. So let's just do that here. To put a 0 here, you can do -2 row 2 plus row 1 into row 1. And then you can put 6 row 2 plus row 3 into row 3. So let me leave this one like, so row 2 is the one I'm going to use for all of this. Okay. I have 0, 0, 0, 0, 0, 0, 0. Okay. And then like -2 root 2 is like, again, it gives you 0, -2, -2, -4. And then this one is 0, 6, 6, 12, good. And then you're adding that to the coefficients of each row, so it's +1, +2, +3, +9, and then +0, -6, -10, -24. Okay, and this is, so you get 1, 0, 1, then you get 5, then you get 0, 1, 1, 2, 0, 0, -4, -12, 0, 0, 0, 0, and we're almost there. We're almost done. Okay, so got rid of, already cleaned column 1, already cleaned column 2. I need to clean column 3. And to clean it, I'll make this a 1. So to make a 1 there, I will just multiply by 1/4 or -1/4. What's that? This one gives you 3. Okay, and then you get 0, 0, 0, 0. Okay. And finally, this to put with this one you can put zeros all above it. So to do that, you just what you can do? What can we do? You would do minus row 3 plus row 1 into row 1, and then you would do minus row 3 plus row 2 into row 2. So I mean, let me just do this, put what it's supposed to give you. Like this is kind of like how people will use it, like, at some point you end up skipping some steps, so you would just like maybe write the result instead of like doing like the middle step where I have been doing, where I put like the operations explicitly. So you would do like, you get 0 with 1, that gives you 1, then 0 with 0, that gives you 0, then -1 with 1, that gives you 0, then -3 with 5, that gives you 2. Okay, and then it's kind of similar here. You got 0 with 0 gives you 0. 0 with 1, it gives you 1. Then -1 with 1, it gives you 0. And then -3 with 2 gives you -1. Okay, so I mean, in practice, that's kind of how people would use these operations. They wouldn't put like a middle step like this one because it just takes too much time. So you kind of will do, like, I think you will end up doing them mentally, but it's just kind of, at the beginning, it's useful to see everything written down explicitly, but then, like, it would just take forever. But here, so what that means is that that now this is raw reduced echelon form. There's no more way to simplify this. This is as best as you could hope. Okay, so if you rewrite this as a system of equations, you get 1 0 0 0 1 0 0 0 1 0 0 0 times x y z equals 2 minus 1 3 0. And again, you can, okay, so that's what happens when you undo the vertical line. That's how it looks like. And then when you do these operations, like, it's super easy. That's the whole point of simplifying. No, that's I'm about to discuss this. This is important. This just is saying x equals 2, y equals -1, right? Z equals 3, and the last equation says 0 equals 0, right? But that doesn't mean like there were only you have to be careful here because in the original problem there were only 3 variables, right? If you notice, like at the beginning of the equations, right? Whoops, here. Like there are only 3 variables. The fact that there's like a 4th equation, that's a different issue. But there are only 3 variables, x, y, and z, right? So what is this 0 equals 0 means is that kind of like one of the equations was kind of redundant. So this just means that kind of like the information of one of the equations was already contained in the others, right? So this just means that well, if you had okay, if there had been a 4th variable here, then that would have been infinite solutions. But we will talk about infinite solutions tomorrow. But yes, but it is just because there were 3 variables here that there are no infinite solutions. Okay, so this just means that there is one of the equations, there was redundant information in the original equations. Okay, because this is giving you the value for x, the value for y, and the value for z, and there's no more choices, right? So this is actually a unique solution. This is a unique solution because there's the only 3 variables were x, y, and z, and I am telling you what those values are. Okay. So here's one way to, is that making sense so far so good? I'm about to tell you how to identify this in a different way, like the unique case, but like I just want to make sure like this is making sense. So what I'm trying to say is that there were only 3 variables originally in the problem, and I'm telling you what the value of each variable is. So I do have the unique solution case. Is everyone okay with that? So now, let me tell you a different way to identify this, which is better, a more useful way to identify the unique solution case. If you look at this matrix, right? What is the rank? What is the rank of this matrix? It's 3. And another way to identify a unique solution case is that the rank of the matrix must equal the number of columns of the matrix. So let me write that down. And that's actually the best way to identify this. So this matrix had 3 columns. That means that there were 3 variables. And if the rank matches the number of columns, then you're done. There's like a unique solution. So let me write it down to finish today. And tomorrow we'll do the infinite solution case. So here's like a theorem. For the system of equations, AX equals B, if the rank of A, if the system is consistent, like and the rank of A equals the number of columns of A, then there's a unique solution. Basically because, but what this is saying is that the rank is the number of non-zero rows. So for each variable, you're getting a non-zero row. So that kind of is giving you like one equation per variable. So this is kind of saying like there's one equation, like, you know, number of columns of A equals the number of variables of the system. of the system of equations, if you think about it. So that's saying, so this is saying that there is like one equation per variable. So that's why there's like a unique solution, right? So you're getting one equation per variable. Is that making sense? Hence the unique solution. So what will happen tomorrow when we do the infinite solutions case is that the rank will be smaller than the number of columns. So that means that many variables need to share the same equation. And so that makes it impossible to find like a unique value for the variables, because there will be like, for example, 2 or 3 variables that appear in the same equation. So there's no way to finish solving for them as a single number. But we'll see that tomorrow. So tomorrow I'll give you an example of that, and tomorrow I'll also tell you how to find the inverse of a matrix using these systems of equations. That's kind of like the last topic, almost like the last topic that I was planning on including for the exam. So, but yeah, we'll finish all tomorrow if that sounds good.
Yes, sir, I have a question.
Mhm.
Could you go back to the system of equation with no solution?
Oh, with no solutions?
Yeah.
Here, this one?
Yes. So for okay, let me see. For the 1, 0, -1, -2, that part, let me see. Could you go?
You mean this 1, 0, -1, -2?
Could you go up a little bit? Because I want to
Oh.
see the most simplified part.
Tell me if I should keep
Yeah,
going
yeah, yeah,
up.
yeah, yeah. At the bottom. So I saw it. So 1, 0, -1, -2, and -7s right here.
Yes.
So why we can keep going?
Oh, it's just because you had a 1 here, right?
Yes.
And you can use that 1 if you want to make zeros here.
Uh,
But also, I mean, actually, once you get to, okay, that's because I just wanted to keep reducing the system. Once you get to something like this, you're done. Like you can immediately say already here that the system is inconsistent. You don't need to actually keep reducing it, because you get 0, 0, 0, 0 equals 1, right? So
Mhm.
this equation already is saying that 0 equals 1. So in fact, you could have stopped here if you wanted to.
Mm.
So I'm just saying that, like, it was still possible to go a little bit further, because you could have used this one to make zeros, but that's kind of more optional. I just wanted to show like all the steps. For the inconsistent case, like the moment you get a bunch of zeros followed by a 1, like, or like something non-zero here, you're done. Like it doesn't matter if you didn't simplify this further, because you cannot fix an inconsistency. Is that making sense?
Yes. And could you also explain one more time the part C?
Explain one more time which part, sorry?
Part C.
Part C?
Yeah.
But okay, so
Let's go
should I keep going down or up?
up. So the C,
Up.
it's whenever a column continues the non-zero entries
Oh,
from
okay. You
the
mean now I get you. The parts like the definition, like.
yes, definition C.
Okay. Like yeah, it's kind of what I was saying, that what this is saying is that it was better to look at it at an example. Let's see. Okay, like this is why I wrote this example. If you look at the second column, right? Oops. If you look at the second column here, the second column has the first one of the second row, right?
Should be, yeah.
So what that means is that once a column contains the first one of some row, it should all the other entries in that column should be 0.
Mm-hmm. Yes.
So you just have, that's why you have to force these two other entries to be 0. But again, in practice, like that's what I was saying, that the definition I don't find it too useful, because once you have done like a couple of examples in these problems, you kind of see a pattern, and the idea is like, wow, you just want to make as many zeros as possible, right?
Mhm.
So with this one, of course, you can make a 0 here and a 0 here, and that's all that you need to know.
Yes.
You see what I mean? So it's kind of like better to just think, I'm going to move from the first column, clean up the first column. Then you try to clean up the second column as much as possible. Then the third column as much as possible. And things. And once you go over all columns, you're done, basically. Is that making sense? So I don't think remembering the definition kind of helps you too much, because once you have solved like 5 or 7 or 8 of these systems of equations, you kind of always see that they're really literally the same.
Gotcha.
Yeah. Is that okay?
And the okay, so could you go down a little bit? Going down. Yeah, okay, stop here. Going up.
Oh, go up.
Yeah, stop here. So for this example, you said that is a good matrix because it's already in the most
Right.
simplified, right?
I already cleaned this one. I already cleaned this column. How could I clean this column? Well, like you could try to put a 0 here, right?
Yes.
But putting a 0 here forces this one to become a -1, right?
Oh, it's still going back. Okay.
You kind of are undoing, I mean, the cleaning process cannot affect the previous columns, right? So to get a 0 here, that can only come at the expense of making something here non-zero. So that's not the principle. The principle is like, once you have your columns ready, you shouldn't go back to them. So yeah, that's why this one was good to go, because there's no way to simplify this further without destroying what you already did.
Okay.
Is that making sense?
Yes. And I have a question. So if we want to simplify another rows, I need to use the another rows to multiples. Rows
Like
if you
if you want to make zeros on a particular row, I mean, you can, okay, so it depends what you mean by simplify. For example, okay. Like, where did I have this? Like, for example, here, like, you know, here when I did -1/5 of row 2, right?
Yes.
I'm kind of simplifying this row because I'm getting ones, right?
Yes.
So this counts as a simplification, and that only uses that same row. But that can never give me new zeros. So to get new zeros, you do need the help of another row. That's the only way to get new zeros. So new zeros can, on a given row, can only come with the help of the other rows. Is that making sense? So that's why you have to take the combinations of the rows. But I mean, you can simplify a row without other rows, but you cannot simplify what you're after is to get zeros. You cannot do that without the help of other rows.
Okay.
So like what I'm saying is that, yeah, if you had wanted like or some, like, again, if you had wanted like a 0 here, there's no way to get a 0 here without the help of one of these other rows. That's all that I'm saying. So to get zeros, you do need to use operation 3 of like combining the rows.
So for this matrix, like the first column is good, and
the first column was already good. Yes.
Yeah.
First column was already good.
We keep going to figure out the second one. So because the second row, it's already have 1 here, that we need to make the rest of the rows equal to 0.
Correct. You can use this one to put zeros here and here. Exactly.
Okay. So can I? Oh yeah, so for the first row, if I want to go to 0, I can just use the 2 minus 2, because if I use the 2 minus 2, I will got a 1. The first numbers go back to -1. So
Right, yeah.
okay.
Yeah.
Oh, that makes sense.
I mean, it's kind of again, it does take a little bit of time to get used to it, but it really is like that's what I was trying to show the Wolfram Alpha thing because like let me see if I can show it again. Really, you can play with the numbers, right? Like so, if you let's say it's a great way to say, okay, I want to play with different numbers here, right? Like let me just randomly put some others once, right?
Yes.
So you put this here. Like say I want like I want them to 4 entries, but then I want another vector or another row. So you can do something like this, right? I change it a little bit.
Mm.
So I now have this matrix, and now you put in a Wolfram Alpha, and you know what the answer should be, and then you just try to see if it works. So it's kind of like, if you're not like, it is useful to do some experimentation when you just like play around with some numbers. You can even start very small. You can start with like 2 by 2 cases, right? Put 2 by 2, and then put like a 5 7, right? Like you do something very simple like that. Once you're comfortable with that, you can like put like a third entry to all of these, so like a 5 and then a 6, and then maybe let's do 1 1 1 just for the sake of it. You put something like that, boom, and then you got a new matrix, and now you know what you should get to. So once you start practicing that way, you'll see that you're always doing the same thing over and over and over and over. So it will get very repetitive, but that's good. So
Okay.
yeah, it's a good way to check and play around with the numbers. To like in practice, like I won't give you too many. You probably already realize that this takes a lot of time because there are many operations you have to do, subtracting and multiplying many times. So in practice, like the matrices I'll give everyone will be like 3 by 3 or 4. I mean, 4 by 4 will definitely be like the biggest that you would ever see. Like more than that just takes forever. So if you are comfortable with matrices of small size, 2 by 2, 2 by 3, 2 by 4, 3 by 3, 3 by 4, 4 by 3, things like that, then you get
Okay.
you have like a good idea of what's going on.
Okay. Gotcha.
Is that okay?
Yep. Thank you so much.
Good.
I think I have no problem with it. Have a nice day.
You too. Let's see. I don't know. Was there anyone else who wanted to ask me something else, or what are we doing?